Great. And allow me to introduce again Dr. Chuck Chung from IBM Quantum. Dr. Chung, take it away. And you're most welcome. Thank you for joining us.
Hi, everybody. First of all, thanks for inviting me to come speak to your group. I'm part of IBM Quantum, and I'm part of the applications team at IBM. And so what we do is we try to find ways that quantum computers can be used and helpful to solve people's challenging problems. And my specialty is applying quantum computers to engineering and manufacturing industries. So let me start with sharing my slide. Let me confirm that everyone can see my slides.
Yep, looks good to me.
Okay, good. So, for those of you who have never seen a quantum computer, this is what one looks like. This is one of ours. This is called the IBM Quantum System 2. To give you a sense of scale, this center panel here, that is where the quantum computer is held. Three separate what we call cryostats can be held in here. It's about the size of an elevator. And these two cabinets flanked on either side of it are where the control electronics are. Behind it is a bank of cabinets that handles things like the cryogenics and the access to the cloud and things like that. Okay, so so let me say that computation is transforming. On the one hand, everyone knows that AI is currently um surpassing the human baseline. What you see here on the left here is a graph from Stanford's AI index, and you can see all these AI models are now surpassing the AI index. At the same time, traditional increases in traditional compute power is slowing. And so what you see on the right is a plot of the performance of the top 500 supercomputers over time. The green dots are the aggregate performance of all 500 supercomputers. The brown line is the performance of the number one supercomputer at the time, and the blue line is the performance of the 500th supercomputer at the time. If you look at the green line here, there's this funny kink in the curve that occurs right about here, about 2013. Before 2013, the slope of this line was about 350x per decade. So HPCs, or supercomputers, were increasing their performance at a rate of 350x per decade. And after 2013, the slope of this line it drops by an order of magnitude to about 30x per decade. The consensus explanation in the supercomputing community is that what happened in 2013 was essentially geometric scaling of the planar FET, field effect transistor, quit working. We had to switch to a more complicated quasi three-dimensional design to the FinFET. This transistor is more capable, but also more difficult to design and manufacture. And so that is a consensus explanation for this drop in rate of increase. Interestingly, TSMC last year introduced the next generation transistor, the GAA FET, because the FinFET is starting to reach its scaling limit. Nobody knows whether or not this line will change slope again, but we should not be surprised. But this chart is indicating that Moore's law has already slowed down, and we know that it will slow down more, maybe as soon as this year, and eventually it will have to come to an end just simply by the laws of physics. As a result, we at IBM we pride ourselves on inventing, as we call, the future of computing. We have a vision where quantum computers, classical HPCs, and AI will all come together in a singular architecture to work together. We see these three modes of compute as not being competitive, but being complementary. We see quantum as being an essential third component to this architecture going to the future. Now, this is not slideware. We have now constructed three of these machines around the world. The first one was in upstate New York at RPI. The second one was at the Riken Supercompute Center in Japan, and the third one is in the EU at the Supercompute Center in Spain. Um, we, our mission at IBM or IBM Quantum, is to bring useful quantum computing to the world and make the world quantum safe. And by the way, we are leaders, but don't take my word for it. This is what several companies have rated us at. We have a fairly detailed roadmap on our plans for quantum computing. There's a lot of information here let me kind of summarize and bring your so first of all, let me invite you to look at this roadmap on our website. But let me also bring your attention to two, I think, key dates, which is in 2026 this year. We expect to demonstrate quantum advantage. It is possible, it's not guaranteed, but we think it's possible this year. And the other date to keep in mind is 2029. This is when the arrival of our first error-corrected quantum computer will become available. So what can you do with these fancy machines? Well, there are generally accepted four main application areas for quantum computers. There are more, but these are the four that I think have the most literature around them and therefore are the most well understood. And they are chemistry and material simulation, combinatorial optimization, machine learning, and solving differential equations. And these all translate into use cases into essentially every industry. Um, so one thing to keep in mind is that the quantum computer, we don't expect to be a substitute for classical computers. We expect it to be kind of a specialized processor similar to the GPU. And the QPU will accelerate at least these four workloads that we see. In terms of feasibility, we think that quantum advantage is possible in the next 1 to 3 years in chemistry and materials and in optimization. Chemistry and materials has higher probability than optimization does, I think, in the next 1 to 3 years, but we think both are possible. Machine learning is a funny space because possible benefits are possible now, but it requires some nuance. I'll go into that a little bit. And the last area is one that's I think there's a lot of interest in is using quantum computers to solve differential equations. Right now, the algorithms require a fault-tolerant quantum computer, but as I said, we're expecting one of those in 2029. So that's the earliest that we expect differential equations to be solved by quantum computers. But depending on your particular use case, it may be later than 2029. So what I'll do is I'll give examples in each of these four application areas to give you a sense of how people are using them to solve problems in industry and what the state of the art is. So let me start, and I'll go almost this order. I'll do machine learning last because, like I said, it's a little bit more complicated story. But I'll start with chemistry and materials. So this is an area that we're excited about because the largest jumps in product cost performance curves typically comes from the introduction from new materials. And so to give you an example of that, this is work that we did with Mitsubishi Chemical on developing quantum algorithms for simulating high energy density batteries. If you look on the chart on the left here, you can see there are a couple of battery chemistries listed here, and the x-axis here is their energy density. You can see, and the bottom here we have the energy density of gasoline. And you can see that most of these battery chemistries have an energy density that's quite a bit lower than gasoline can do. But there's one battery chemistry, lithium air, that can approach the energy density of gasoline. Lithium air batteries are challenging to develop. There's a lot of side reactions that are undesired. What we did is we modeled with our quantum computers the primary reaction in the battery, this reaction depicted here. We modeled in particular the reactants, the transition state, and the products. We calculated the ground state energy. This blue line is the classical Hartree-Fock calculation. The orange dotted line is the exact solution. And then the red and green lines are the outputs from our quantum computers. And so this paper is pretty old. It's about 5 years old now. But what you can see is even back then, we were getting fairly close, qualitatively close to the exact solution back then. Now, the challenge with developing things like lithium air batteries is that it takes a long time. It takes 10 to 20 years. Typically, decades is the characteristic time. And the reason why is new material development is typically dominated by empirical trial and error methods. Computational methods are used in sort of a limited way here, but they have challenges with a number of materials, such as materials that involve transition metals. So we have done more recently, we've done this, we published this paper on looking at another reaction in batteries. This is looking at the surface interface, the solid electrolyte interface. This interface is one of the controlling factors in battery lifetime. And what you see here is we modeled this reaction up here. On the bottom, you can see the reactant, and the product of a quantum algorithm versus, or two quantum algorithms versus several classical algorithms. The quantum algorithm that performs the best is this EXT SQD, the green diamonds, and you can see it is as you increase the active orbital space and essentially the size of the simulation for these chemical entities, you can see that the green line is performing well with respect to the reference here, which is this CCSD. I'm sorry. Yeah, the CCSD method. The bottom is looking at the difference between the EXT-SQD quantum algorithm compared to the benchmark, which is this CASCI or complete active space configuration interaction. You can see that this green diamond has the lowest error compared to the other algorithms compared here. It stops at 14 orbitals, not because of the quantum computer, but because of the classical computer. Essentially, the computational workload for this material for this algorithm grows quickly, and at least on our computers we're using for this paper, we were unable to model this above 14 active orbitals for this particular system. So let me be specific in terms of what I mean when I say what we're doing. When I say we're doing chemical and material simulation, what we're doing is we're solving the Schrodinger equation. If you're not familiar with the Schrodinger equation, it is the quantum generalization of Newton's second law, F equals ma. So it's a powerful expression. In particular, what we're doing here is we're solving what we call the time-independent Schrodinger equation. So we do a little bit of algebra. We separate the variables. We take only the spatial component of this problem. In other words, we're looking at the long-term steady state status of the system. The solutions of this time-independent Schrodinger equation are the eigenvectors. They describe the spatial distribution of electrons around a molecule, and the eigenvalues, they essentially describe the energy of that electron distribution. In this paper, what we have developed is an algorithm called SQD, sampling-based quantum diagonalization. This is one of the first algorithms that takes advantage of both quantum and classical computers working together. And so we modeled this molecule here, this iron sulfur cluster. This is a molecule that is critical to mitochondrial processes. And what you can see in the plot down in the bottom is this orange line represents a eigenvector for the system. The y-intercept corresponds to the eigenvalue for that system. Back in 2024, when we did this work initially, you can see that the energy was described in this pink line here. And in about a year, we're able to get to lower that energy. Lower is better in this case. To here, we're not quite yet exceeding the state-of-the-art classical method, the DMRG method here at the bottom. But you can see the rate of increase over a year. And it's this rate of increase that makes us think that surpassing state-of-the-art classical methods is possible within the next 1 to 3 years. Now, as I said, SQD is one of the first algorithms that combines both a quantum and a classical computer working together. The way the algorithm works is you initially choose some molecule to simulate, and then you select what we call a basis set. In chemistry, it's you essentially choose a sort of space in which you express the solution. This is at the start of this process, we don't know what configurations the electrons will occupy in this basis. And so we use 77 qubits on a quantum computer to essentially simulate the system. And before we use the quantum computer, the solution space is essentially 2 to the 7 by it's a matrix that is the size of 2 to the 77 by 2 to the 77. This is about a matrix the size of 10 to the 23 by 10 to the 23. So it's a very, very large matrix. It's a matrix of a size that is not solvable or diagonalizable on current classical computers. So what the quantum computer does is essentially subsample or samples this space to find the most important configurations that the molecule's electrons occupy. And then outputs that. And we do a little error mitigation here. And then what it does is essentially reduces the matrix size from 10 to the 23 by 10 to the 23 to 10 to the 8 by 10 to the 28. If we've chosen our basis set well, this matrix, the resultant matrix is nearly diagonal, but not quite diagonal. But it's now of a small enough size that we can complete the diagonalization on a high performance computer using the Davidson algorithm. Um, State of the art now with SQD. This came out, like I said, this algorithm came out in 2024. Just last week, we've now scaled up this algorithm so that we are now modeling a 12,000 atom protein. The way we do that is that we essentially break up the molecule into smaller bits, and then the quantum computers handle the larger, more complex fragments. The classical computers handle the smaller, easier fragments, and then the classical computer also reintegrates all the fragments back together in order to, in this case, we're calculating the binding energy of this particular protein. Another example in the solid state realm is this experiment we did simulating neutron scattering of a magnetic material. So the magnetic material is a 1D material, as sort of depicted in this diagram. In the experiment, what's done is neutrons are shot at this crystal. And what we look at is we know the energy and the momentum of the neutrons coming in. We look at the energy and the momentum of the neutrons coming out. If you do the experiment, you get this distribution in momentum energy space. What we did is we modeled the excitation of the neutrons on this 1D magnetic lattice using the Heisenberg model. What you calculate with the quantum computer is the Green's function. And if you take the Fourier transform of the Green's function, you recover this energy diagram or this phase diagram. The experiment you can see is depicted here in the upper image, and the results of our simulation are depicted in the lower image. And you can see qualitatively the two results match each other quite well. We have a number of quantitative metrics that we use. Some of them are statistical, some are image. Some of these characterize images. At any rate, what you can see is that there's generally good quantitative agreement. We also compare with a simulator instead of using as opposed to using a quantum computer, and you can see the simulator generally has marginally better results because of the lack of noise in simulators. But again, we see quantum computers as they progress. The noise will get better, but also in addition to that, the size of the simulation will also increase beyond a point where simulators can't be used. Um, in this particular case is a special case because we're using a 1D crystal. 1D crystals are easier to simulate than say 2D or 3D crystals. And so we're at the status of the experiments are such that we are at this frontier where quantum computers are almost at the point where they can surpass what classical computers can do. So we're kind of at a verification process or a verification stage of the output of the quantum computers, because pretty soon we believe that quantum computers will be outputting results that classical computers will not be able to verify. Before I move on to the next section, are there any questions on this section? Okay.
I have a question, Dr.
Yep.
Chung.
Yep. Go ahead.
So, would it be it's sort of a brute force kind of a question, so forgive me
Yep.
for it being fairly unrefined, but I think it's fair to say that, and you can correct me if I'm wrong, and please do so. I
Yep.
think it's fair to say that certain problem spaces that are well aligned to quantum computation as a solution
Yep.
um, don't necessarily improve by throwing a larger quantum computer at it with more qubits. Do I understand what I'm learning in the popular press that it's what will really benefit time and expense to come to a solution is integrating with HPC and maybe some of the other computational tools that are, hands right now, AI, et cetera. So would you think that that's a fair assessment? And if so, I'm wondering what sort of time investments for QPU time some of these use cases have required.
So generally, I agree with you. I can give you, for example, a story with regard to chemical and material simulation. I said that we believe quantum advantage is possible in the next 1 to 3 years. Had you asked me this question before the discovery of the SQD algorithm, I would have said that uh, quantum computers will be able to go beyond classical computers in more like post 2029 timeframe. Um, and what changed with the SQD algorithm is that the estimate before SQD was based on using just a quantum computer. What SQD essentially did was it found a way to combine a quantum and classical computer working together to solve the problem. And that's what brought in the advantage timeframe from, post 2029 to maybe this year. Um, so that let me say also that we see that it is these sort of quantum-centric supercomputing algorithms that we think is a particularly rich area to do research in. Previous to the construction of our first QCSC, quantum-centric supercomputer, that occurred in 2025, everything had to be theoretical. But now that we have more than one of these machines, now we can actually do experiments. And if you analogize where quantum computers are to the history of classical computers, I would say that quantum computers are sort of in the early mainframe era of the classical computers. So sort of like late 40s, 1950s sort of era. And if you sort of think of the status of algorithms at that point, we didn't know many of the most important algorithms that we have now. So, for example, the fast Fourier transform was not known. Finite element method and the computational fluid dynamics were those algorithms were not known. All the AI models that are so transformative today, none of them were known at that point. And so, we think that investigating algorithms where the algorithm is able to both use a high performance classical computer and a quantum computer working together is going to be particularly fertile area for research in the near future.
Yeah,
Does
thank you
does
for
it?
that. That's
Yep.
yeah, that was marvelous. Thank you. A lot of stuff from certainly me to chew on. Before you go on, one more
Yep.
question
Yep.
from Prakashan. It's in the chat frame.
Okay.
Prakashan asks, how much compute resources does DMRG method need for the example that you've shown?
I don't know, actually. That's a good question. I think I do have papers listed for all these slides. It may be in one of these two papers. I think they stated, but I'm not 100% sure. It's been a while since I've read these papers. So I don't know right off the top of my head. There was a second part to your question, Jim, which was how much time do we need on the quantum computer? I can tell you that the time is dominated not by the quantum computer, the time is dominated by the classical computer. For this particular problem, I think in the original paper, it took about 45 minutes on the quantum computer. And on the classical computer, it was taking like tens of hours to do the final diagonalization. Now that has changed as of the beginning of this year. What we essentially did is we parallelized the Davidson algorithm so that it could be executed more quickly on GPUs. And so now we have come up with workflows that sort of balance the workload between the quantum computer and the classical computer, such that, for example, in the Cleveland Clinic or this protein modeling paper, the quantum computer and the classical computer are pipe. The workflow is assigned and pipelined roughly so that both machines are used as fully as possible. And so it's the workload is better balanced between the two types of machines now. But this is where the frontier is. Where I mean, this is only the first algorithmic example of this, and this is as a result, that's the only algorithm for which these workload balancing algorithms are designed. But we are, like I said, we think that there are many more possibilities in this space, and of course, the workload balancing is likely going to have to be different for these different algorithms. Let me give you a second example. So SQD was this chemical material simulation was the first QCSE algorithm. There's a second algorithm, class of algorithms, which is cryptography or RSA code breaking. And there was a series of papers that essentially reduced the quantum resources required in order to break RSA encryption. It reduced it by several orders of magnitude, and the fundamental trick there was that the authors figured out a way to combine a quantum and classical computer working together to perform that computation.
Yeah. Well, thank you very much for
Yep.
that. Terrific insight. And I wish, excuse me for being so forward, but I just want to give us a reminder of time.
Yep.
It's now 12:33. So thank you. Please
Uh,
continue.
what time do we need to end?
We typically like to wrap up around a quarter two, but
Okay.
it's so fascinating. I would love to ask for everyone's forgiveness for me to start late. If we could just keep an eye on the time and
Okay.
allow for some Q&A, maybe around 12:50, 12:55 Eastern, we could try to wrap up.
Okay, I will try to move through these quickly. I don't think I have, I think I probably have more slides than we have time, but we'll try to go through as much as we can.
Thank you very much.
Yep. So let me talk about the second area, which is optimization of search. So the landscape of quantum algorithms is that we have kind of three categories. There are those that are provably exact. In other words, they're guaranteed to return the global optimum.
Mm.
There are those that are provably approximate, which means that they won't necessarily return the global optimum, but there's some guarantees, such as in this algorithm, the result you receive will be within 87% of the global optimum. And then there are the heuristic algorithms. And this is where the bulk of classical algorithms work. They're essentially rules of thumb that can work pretty well. Like, for example, in a traveling salesman problem, it's able to solve within 2% of optimality, like the traveling salesman problem to every city on the planet. Um, but there are no guarantees. These are just heuristics. And we believe that whereas the first two categories a quantum computer can bring advantage, it will require a fault-tolerant quantum computer. So it'll be post 2029. Near term, we believe that there are also quantum heuristic algorithms. And we think that this is a place where quantum computers may be able to surpass classical algorithms. Because there are no a priori guarantees, the only way to see how well classical algorithms works is to try them out. And so we published this paper that essentially benchmarked um, a bunch of different problems on state-of-the-art classical algorithms, and we identified 10 problems, the intractable decathlon, where classical computers they start to lose optimality at smaller problem sizes. And let me give you two examples. One is a Steiner tree packing problem, and the other one is a portfolio problem. The Steiner tree packing problem is directly applicable to microchip design. In microchip design, 90% of the energy dissipated in the microprocessor cache is simply in the wires, and caches now consume over half of the majority of microprocessor energy. If you could find a shorter route to connect all these circuits, then you are directly addressing the major source of power dissipation in these chips. This is modeled by the Steiner tree packing problem. Essentially, the Steiner tree packing problem is that you have a set of terminal nodes that have to be connected through a set of intermediate points, the Steiner points, but you don't have to use all of them. You just need to use some of them. The Steiner tree packing problem is a variant on this in that you have multiple Steiner trees connecting through the same set of intermediate Steiner points, and you want to find the optimum set of Steiner trees using these points in the middle to connect these outer points. And so this is for an identified problem, for example, where a quantum computer could surpass a classical computer using heuristic methods. Another example is the portfolio problem. This is a paper we published with Vanguard. In this paper, we looked at a bond portfolio with 109 bonds. Each bond is either in or out of the portfolio. So we have 2 to the 109. That's about 10 to the 30 or 40 possible portfolios. Out of that huge number of possible portfolios, we find quantum algorithms that are finding a portfolio that is within 0.5% of optimum. Um, as this problem scales larger and larger, we do believe that a quantum computer will eventually has favorable scaling characteristics and therefore will surpass what classical computers can do. Vanguard tells us they can do about 1,000 with their classical computers right now, and so we believe and the traditional mapping is one binary variable per qubit, and we have about somewhere between 100 and 150 qubits right now on our machines. We do plan to release 1,000 qubit machine in about 2 years. Um, One other point on object optimization, another place where we believe quantum computers will find advantage is in multi-objective optimization. What you see is some benchmark times for the max cut problem. This is a graph problem where you're trying to cut it and find the maximum number of edges that you're cutting in between the two halves. For one objective, it took less than a second for a classical computer to solve, but for three objectives, it took 3 minutes, and four objectives, it took 5 hours. And so what you see here is a Pareto front where we have objective 1, 2, 3 on the three axes, and we were looking for the surface of optimal solutions. What you see on the right is a benchmark of classical and quantum algorithms. You can see that the quantum algorithms, these are simulated, are outperforming all the classical algorithms. this curve, this purple curve here is actually the quantum algorithm executed on hardware. So right now, executing on par with the state-of-the-art classical algorithms. But as our quantum computers improve, as the noise is reduced, we believe that the quantum curve will extend towards this red line, the optimal solution. By the way, with quantum advantage, we don't think quantum advantage is going to be this like singular event. We believe that it's going to be it's a testable hypothesis. It's something quantum advantage is going to be one of these things that will have to achieve consensus by the community. And so we by no means feel that we have any position or authority to say yes, this is advantage or no, this is advantage. What we have done, our role we see instead is to facilitate that community discussion and consensus building. And so we have this website where we allow people, anybody can contribute results, both classical and quantum, to compare a database so that people can do an apples to apples comparison to see, how do the best classical algorithms perform versus the best quantum algorithms perform, and thereby maybe the community can reach a consensus on whether or not advantage has been demonstrated. The next area is differential equations. This is this is where one of the largest computational workloads are experienced. This, I think, solving differential equations and solving the Schrodinger equation for quantum systems is, I think, the two largest workloads for, I think, the national supercomputers. This has differential equations have wide application. Um, the sort of the landscape of quantum algorithms for solving partial differential equations are that we have kind of three categories. There are linear partial differential equations, the weakly nonlinear, and the strongly nonlinear. The linear and the weakly linear can be solved with both PD specific methods as well as general quantum linear solvers. Weakly nonlinear systems can go through a linearization and also be solved the same way. Strongly nonlinear, we don't think there is a general algorithm, quantum algorithms to solve these, but we do see PD-specific methods possible. Let me talk about what we see possible with the linear algorithms, since they're nearer term. Oh, by the way, both of these will require a fault-tolerant quantum computer. Um, so this is the general solve workflow. You specify a model, you then generate a model, and then you discretize it. You essentially capture the representation of this discretized model in a large set of linear equations, essentially a matrix. And if you you essentially multiply a matrix A, which represents the model, times X, which is the model's displacements, and you essentially get the forces. So this is F equals Kx. This is spring constant. That's the spring equation. But you're typically not interested in the forces. You're typically interested in the reaction. So in order to find the reaction, you have to invert this matrix A, multiply it by the forces, and you end up getting the model's reactions to those forces. It's this matrix inversion that is the time consuming step. There is a quantum algorithm that behaves quite differently from the classical algorithm. The plot here, you see the y-axis is number of computational steps, and the x-axis is size of the matrix or the vector. The classical algorithms have a polynomial scaling, so they're all straight lines of different slopes on this graph. There is a quantum method, though, that scales not polynomially, but logarithmically, and that's this blue curve here. And this difference is literally an exponential acceleration of the matrix inversion problem. One of the ways to interpret this blue line is that it's basically saying that a simulation that requires 1,000, say, elements is not that much faster than, say, a simulation that has 1 trillion elements in it, which is kind of amazing if you've worked with these kinds of solvers in the classical realm. And there's such a tight a relationship between matrix size and computation time that we just it's assumption when in going in solving these kinds of problems. But this quantum algorithm opens a door to very, very large potential differential equation systems, or solving differential equations for large systems. And so now, naively, if you're going to apply this, you would have your classical computation. If you go back to that workflow, you have your discretized system, and it passes the matrix into the quantum computer, and the quantum computer performs a matrix inversion, and it passes this solution back out to the classical computer. But you have to pay attention to these interfaces between the quantum, the classical, and the classical computers. They are slow. And so if you look at this in a little bit more detail, the interface here The matrix has to be sparse in order to be efficiently loadable. It also has to have a good condition number, although this is not a quantum thing, this is a matrix inversion thing. And then on the back side, the way the solution is stored in the quantum computer is stored as a superposition among all the qubits here. As soon as you take a matrix, as soon as you take a measurement, that superposition collapses, and you can essentially get one scalar value out at most, or maybe a few scalars if you run this a couple of times. And so this output restriction severely limits like what a quantum computer can do for this class of problems. And so it's in order to preserve the acceleration, you have to pay attention to a couple of things. You have to sort of realize that the correct question has to be identified. It's not going to be the same question. It's not going to be the same question as we pose to classical computers. The workflow has to be reconceived, and the role of the quantum solvers in the entire design process has to be reconsidered. So let me give you an example. This is a paper published by Toyota, performed these computations on our quantum computers. What they're looking at is they basically say, if you can only ask the quantum computer one question, you probably don't want to know like what is the temperature at a particular point in space or what is the stress at a particular point in a model. What you really, really want to know is what is the best design. And so they use a design framework called topological optimization, and all possible designs are captured in this framework. So they're asking what structure has the best thermal conductivity here. The design space are these four lines and these two diagonals, so 6 lines. And they essentially look at every possible design. So there are 2 to the 6 or 64 designs, and and then what they do is they solve the heat equation essentially for these structures. And so in the classical method, you would do it sequentially for each possible design. In the quantum method that Toyota devised, they essentially do these all 64 designs in parallel, and then they extract out the optimal structure. And so this is how, one would use, if you could only ask the quantum computer one question, you're not really interested in the temperature, for example, at some point in the design. What you're really interested in, what is the best design? And Toyota, I think very cleverly in this paper, figures out a way to use a quantum computer to help answer that question. And the way they do it is going back to this workflow. If you can do one model, if you construct your matrix like this, sort of block diagonal, you can essentially run many, many models in parallel. And what this opens the door to is essentially simulating multiple designs under multiple tests in order to identify, for example, which is the best design. It can be highest performance design or lowest cost design or lowest power design or whatever in order to use in order and in the design process. And so the what this changes is the role of partial differential solving in the design process. Typically, these simulations are so expensive that we do it at the end of the design process, and we use it only for like 1 or 2 designs. It's used for design confirmation, essentially. And what Toyota is proposing is that we use the quantum computer not at the end of the design process, but at the beginning of the design process, where we're using it for design exploration, and there are many, many possible designs, and we're asking the quantum computer to help us identify the best design. Okay, let me get to my last section, which is in machine learning. As I said, this is a little bit, the story is a little more complex here. A lot of people, we see AI and quantum computing as complementary technologies. AI is really kind of an algorithm, and quantum computing is really kind of a hardware. It's also an information science. But anyhow, we see them intersecting in multiple ways. For example, you can use a quantum computer to generate data that could then be used to train an AI. So, for example, if you want to find the optimum solution, like in those optimization problems, if you change the problem around and solve multiple problems, different versions of a problem, and you use a quantum computer to find the optimal solution to all those versions, you can then use those to use an AI, for example, to generalize to all sorts of problems in that class. In training and inference, we're using quantum machine learning models. Typically in agentic AI, there's some sort of action that's required. Again, you can use quantum optimization to identify an optimum response. There are some papers looking at accelerating the training, the backpropagation calculation using quantum hardware. Let me talk about this quantum machine learning models. And it kind of captures in a nutshell, like why we say advantage is possible now. Let me not use the word advantage. Let me say benefit is possible now, but it requires nuance. So this is a paper we released with HSBC. This is a large bank. What we did is we basically developed a quantum classical model, uses a quantum computer and a classical AI together to see up to 34% increase in accuracy, up to, it can be as low as zero. And in the particular case, what we're doing here is we're predicting the bond market's reaction to a bid. So the bond market, there's a bond that somebody's selling. Um, all these dealers in the market can decide whether they want to bid on the market, bid on the bond, or they can wait and essentially look at it, watch other bids and see whether they fail. And if they fail, you have more information about what a successful bid would be. And we essentially used a quantum computer to do a data transform, which then was, and that transform data was then used to train a classical machine learning model, which then the dealer could say, okay, if I bid this much on this bond, what is the likelihood that it will be accepted? And as I said, we saw up to a 34% increase in accuracy. Now, so why isn't this quantum advantage? Well, first of all, machine learning doesn't really work like that. Nobody says this machine learning model will forever outperform every possible future machine learning model. Well, that's just not the way it works. We typically in machine learning say on this particular data set, this is currently the best performing model. The other reason, though, is that while these results are replicable and reproducible, we don't really understand why we're seeing an accuracy advantage. And so we don't know how robust this is. We don't know how generalizable it is. And it's kind of in IBM's DNA too. Like we're a bunch of mathematicians and physicists and engineers. We were like, if we don't understand something from first principles, we're kind of uncomfortable publishing it. But HSBC wanted to publish it, and we're like, okay, we're not going to stop you from doing that. But anyhow, but this is what I mean. Why benefit is possible now, but it requires nuance because we don't really understand what's going on here. I have a second example here, but maybe in the interest of time, let me skip over it. I have another section on strategy considerations, but again, let me skip over it and let me go just questions and answers so that in our remaining 10 minutes. So,
Dr. Chung, that was marvelous. Thank you. Yeah,
yep, yep.
please, questions are most welcome and encouraged. A lot of good feedback, Dr. Chung. Lots of
Oh,
folks
good.
really enjoyed your talk. Thank you
Oh, good.
again.
I'm not able to see the chat, so if someone could read the questions, if there are questions.
Yeah, I've not seen any new ones come in.
Okay, all right, that's fine. Oh, I see one. When you refer to the number of qubits, did you mean logical qubits? Well, I mean, for us, it's really whatever the algorithm requires. So it can be either physical or logical qubits. But for these, for example, in the differential equation space, the number of operations we need to do is so long; those require logical qubits. In the optimization and chemical materials, chemical and material simulation space, we're using physical qubits right now to do that work. And so in that case, we don't need so many operations on them, and we're able to use physical qubits. So it really depends on the application area. It depends on the number of operations you need to perform on the qubits as to whether or not you need physical or logical qubits. Um, Considering the immense energy demands of classical HPC, especially for AI, is IBM also evaluating the energy efficiency metric when computing quantum computing use cases against classical approaches? Um, we are. I can tell you, though, that it's not really a question that occupies us because the order of magnitude energy that in our quantum computers is like hundreds of kilowatts. I mean, it's basically most of it's from the cryogenics. It's basically that elevator-sized refrigerator. It's a big refrigerator. It's an industrial refrigerator. It's cooling down to 15 millikelvin, so it's a particularly high performance refrigerator, but it's just a refrigerator. And the thermal workload from the quantum processors is low. It's a reversible process. No information is lost, so it's not dissipative, and so there's not a lot of heat created intrinsically by the quantum operations themselves. As a result, we don't see the energy requirements for running a quantum computer to increase very much per elevator-sized space. As you add more quantum computers together, which is one of the ways we'll get to our error-corrected computer, that power grows linearly per elevator-sized case. And I think for our quantum computer in 2020, our fault-tolerant quantum computer in 2029, I think we're going to use like 6 or 8 of those. I think that's approximately the size of it. So, you know, it'll increase by maybe an order of magnitude by that time. Um, Okay, what kind of error correction method does IBM use currently? So the surface code was kind of hopeless, to be perfectly honest. The scaling is terrible. And the scaling, I mean the ratio of physical qubits in order to create one logical qubit. And so we published a paper a year or two now ago where we essentially discovered a class of error correction codes called LDPC codes. This is based on the old classical LDPC codes. LDPC stands for low density parity check. And what we found is that those are like uh, several, I think they're 1 to 2 orders of magnitude more efficient qubit wise. And so it basically reduced what was previously estimated a football field size quantum computer to do, for example, to break RSA encryption. Um, to something more like the size of a 1950s mainframe, like a large room sized quantum computer. Large, certainly challenging engineering wise, but something that's feasible. And we just released a second paper, or we've released more than 2 papers, but we just released another paper last week, I believe, where we're looking at concatenating codes. In other words, the code used directly on the qubits is an LDPC code, but on top of that, we have another error correcting code. And the two together, working together, I think further makes it even more efficient. Another question. What predicted impact will quantum computers have on the effectiveness of classical computers, such as materials and wire pathing optimizations? Um, so, I can tell you that, as I showed you earlier, that Moore's law is slowing down. One of the big challenges there is no longer the transistor. Well, the transistors are no longer the um, main delay in signal propagation. The main delay is actually due to the wires connecting transistors. Transistor gets the delay gets faster as the transistors get smaller. The wires get slower as the connections get smaller, and so that's now dominating. So that's the focus of a lot of research in the semiconductor world. I can tell you that there are um, advanced materials that can reduce that time delay, and one of the ways a quantum computer could help accelerate that is by essentially instead of trying to shortcut the trial and error process that's required for developing new materials. So instead of starting with many materials and trying each one of those one by one using experimental methods, we see using a computational method to essentially pare down that large universe of possible materials to say like your top 3 or top 10 or something like that. And then just look at those materials with experimental techniques to eventually select, for example, a material that is going to be the highest performing. Um, Same thing with the wire pathing. The optimizations, if you find a more efficient, a shorter total path length for the connections and wire optimizations, that will reduce the energy dissipation and also, by the way, reduce the signal delay in microprocessor caches. And that is another way that quantum computers could improve classical compute.
Dr.
What?
Chung, I think we've got time maybe for one more.
Sure,
If you wouldn't mind addressing Max's question about the advantages of true quantum compute versus simulation. And
mm,
there's a question from Wayne Smith and Trevor. I'm going to copy those, and maybe if you wouldn't mind, I'll pass them along to you for
sure,
any follow-up you might have later. So if you can wrap up with this final question from Max,
sure.
that'd be awesome.
Yep. What is the major advantage of running computations on real NISQ quantum machines compared to quantum simulation? Well, I think it's mostly a scale, and simulators typically top out like my laptop will do 30 qubits or so. I think state of the art, like national scale supercomputers will do 50 or 60, maybe 70. Um, if there are some certain assumptions that you can make. And that's kind of where they top out. We have now quantum computers that are 100, 150 qubits, and so we're able to run computations on them that are essentially not simulable, at least not efficiently by classical computers. And so as a result, that I think is the major advantage is essentially the size of your computation, and therefore the complexity of your computation performed on NIST machines will outpace anything that a simulator can do. We, by the way, passed that benchmark past that milestone in 2023, where we're executing calculations that were essentially unsimulable by simulators. Okay, does that
Well,
answer?
Dr. Chung,
Yep.
thank you so much.
Yep.
It has been a pleasure listening to your talk today and addressing our community's questions. So, bravo, and I'm
Thank
very
you.
appreciative. So, thank you, Dr. Chung. Thank you to IBM Quantum as well.
Absolutely. Thank you for having me.
Have a good afternoon, everybody, or the rest of your morning. And I'll try to follow up with Dr. Chung on a couple extra questions if Dr. Chung's so willing. But thanks again and enjoy the day.